Is Joshua Anna not junior? Hello.
Evening, everyone. I hope you can all hear me. Without wasting any more time, let's just get right into the session. We don't know what ECG will do. Welcome once again to another makeup session. Our last session for this year, 207, we had a few run-ins due to the lights out and all that. Today, I'll make up for that and then perhaps even more. Let's get right into it. So we're looking at finding your place using that's in terms of the cache and then memory using different mapping methods. And one of the few things that we learned were the different types of mapping there were. We learned about the direct and then associative and then the set associative. We looked at concepts like the hitting and missing. Hitting is when data is found on the fastest cache that is being used. And then missing is when the data has to be retrieved from the RAM. And then we looked at how the cache is faster because it makes use of locality of reference. And then the types of locality of reference are temporal locality, which works with time, and spatial locality, which works with displacement or the distance of one data value from another. Basically, it's so these were things we looked at the last time. It says if a program accesses a variable and is likely to access it again very soon, then which principle is this? And then we learned that if it's likely to access it again, if it has accessed it once, that is what do we call it? Something that has to do with time. So that's temporal locality. And then we also said if a program accesses an array element, it's likely to access the next element. This one has got to do with things in the same space, so that's spatial. And cache memory exploits reference, locality of reference to keep data ready and then make the operations of the CPU faster. And then we looked at the mapping, where direct mapping. We know that in direct mapping, since one data value is pushed to a particular, what do we call it? Line data of cache, right? There is the need for specific addressing for the data so that the data will not be left stranded and it will go exactly where it is meant to be. For that reason, the data value is split in three particular parts, and that way it can be easily retrieved from the cache, like easily identified, and then sent to CPU when it is needed. We learned that it's broken into three regions. That's the tag, the index, and then the offsets. Then the tag tells us the specific block that we are handling, whether it's block 45 or block 12. The index finds the row or the exact line in the cache where that data is going to be held or is being held, where the offset, on the other hand, finds the exact bytes within the line where the data is being held that we will find the needed data. So there, you remember the address is split into a tag, the index, and the offset. Putting them together is what gives you the full address for the data being stored. So we talked about these ones. The rule of direct mapping is that everybody has a particular place to be. So like in a classroom, everyone has a particular seat to take. This means if you come and your seat is taken, you fight it out with the person that has your seat. Right. And then the trade-off is that since it's fast and easy, that's for the positive side. It's fast and easy because you can easily map data to a particular line without much searching. Whereas the conflict of the cons is that you thrash. This means when two data values have to go into the same space, due to the limited size of the cache, you are going to have to discard one to accommodate the other. I believe you can all hear me, right? Raise hands if you can hear me. Yeah, please, can you hear me? Give me a thumbs up or something if you can hear me. Mr. Richard. Okay. All right. All right. Mr. Richard, is that a question or you can hear me? Wait, I'm coming on. Is it that my ports are not connected because I can't hear you speak at all?
We can hear
Oh,
you.
okay. Oh, oh, okay. All right. That's good. That's good. All right. Let's proceed. So then, as we were saying, the cons or the disadvantages of the direct mapping is the fact that due to the fact that every single data has a particular place to be, yes, we are dealing with limited slots, then there is the possibility of three or more data that are needed at a time being having to be stored in a single cache line. What this means is that the CPU will now have to try prioritizing, but since they are all of equal importance, some will have to just be casted off or thrown away, and then one will be kept at a particular time. So that is the disadvantage of direct mapping. We looked at this the last time. We looked at how the okay. Mr. Joe, I've seen your request concerning It's Mr. Joel here, the DCIC 203. So you don't worry, I'll give an explanation to that. The assignment, right? I'll give a little explanation to that today. Don't worry. All right, let's proceed. So please, Mr. Joel, did you get that? Is Mr. Joel in the session with us? Joel. Okay. All right. So you give me a little this and let me talk to him. Guys, please give me a minute.
All right.
Okay. Right. So we looked at the way the data is broken down, the address of the data that is going to be held or is being held and is retrieved from cache is split into indirect mapping. There's the tag, there's the line index, there is the word offset. The tag is the most significant bit. It means it has the greatest value, whereas the offset is the least significant bit. We looked at how to calculate these separate things when you have been given specific data. So it says we looked at the different types of mapping, fully associative, where you can set anywhere you want. The pros are that it has the best utilization of space because there is almost no messes. Every single place, as far as it's free, you can go and take it and sit. But then the disadvantage is the fact that it's very slow because the CPU has to search through its entire cache space to find a particular spot where there is a free space so that the data can be assigned that space. So Set-Associative does a combination of both and is the best since it balances the flexibility of the fully associative where you can set wherever you want. However, it restricts it to a smaller region where you can only use a particular row. In that row, you might have different cache sets where a single data can go to every single one. So every data can go to a row and then choose from a set of cache memory spaces or cache lines to be and to get stored in. However, it is different from the fully associative because fully associative, you can go wherever, but this one you can go only to particular lines. So that's the set associative. And these are images to show that. And then we talked about this. So let's go back on what we learned here the last time. So we learned in direct mapping, since the data has to go to particular places, it's important that some regions of the data are known, basically, so that it can be easily led to the particular place where it has to be stored, and also easily retrieved from that particular spot again. So now there's a question that we use. It says, suppose you have been given a 16 megabyte RAM, and you're supposed to map it to a 64 kilobytes cache using direct mapping. What this means is that we are moving data that is coming from a 60 megabyte RAM, and the only data that comes from that should go straight to our 64 kilobytes cache. We learned that the first thing you want to do is convert all these values into their powers of 2, right? Into the powers of 2 that they represent. And after doing that, we calculate all using what we know concerning the formulas. So we'll do some questions. Yes, I know last week because of the on and off, it was a little hard to follow. We'll do some questions again. So we learned this. With this one, it says the RAM size is 16 megabytes. The cache size, on the other hand, is 64 kilobytes. And then it has converted cache size to bytes. We need a block size, but for this question, it was not given. So then we assume that, let's say the block size is 4 words, which means 16 bytes. And that is equivalent to 2 to the power 4. And then we calculate the bits. So calculating the bits, that will be the offset, the line index, and then we subtract that from the total to get our tag. So we start with the word offset. It says the word offset is what we call it 4 bits, and we know how this is, right? We know that word offset is log base 2 of the block size. And then the line index, on the other hand, is going to be cache divided by the block size, and then we get the value. And finally, we subtract all of that from the total, and that gives us the remnant tag number. So let's look at this. Do you remember the exact formulas that we used in working these very problems? The lesson went fast last week, but I'd like to believe you picked a few things so that we won't have to run through all the examples. Okay, so let's take our main memory is 32 kilobytes. The cache size is 1 kilobyte. The block size, on the other hand, hello, can you hear me? All right, sorry. My network broke up for a little bit. Right. So let's convert all the values that we've been given here into their corresponding, what do we call it? Powers of 2. So yes, let's go. Let's start with the first one, 32 kilobytes. What will 32 kilobytes be in powers of 2? So we know that, what do we call it? For 32 kilobytes is equivalent to 2 to the power 15 bytes, if I am not mistaken, for the kilobyte. That's basically 32 times 1024 bytes, right? So that's going to be our main memory. Let's use our M for that. That's our RAM. That's going to be 32. It's the same as 2 to the power 15 bytes. That's in bytes. For our cache, 1 kilobyte is equivalent to 2 to the power 10 bytes. Then at the end of the lesson, I'll give you a chart for these things, and so that you can keep them in mind. Then our 16 bytes, 16 bits is equivalent to, all 16 bits be equal to. I think we looked at it in our previous lesson, so someone should join, share with us. Right.
Two
You want
to
to
the power 3.
2 to the power
3, or is it 4?
is 4. It's 4. 3 is close, but it's 4. Yes, so it's actually 2 to the power 4. That's a good try. All right, so then with this in mind, we can now start finding our offsets, our tag, and whatnot. So I'll use O for my offsets. Let's start with our offsets. We learned that if you want to find the offsets, you need a log2 of the block value, right? So log2 of block is basically log2 of 2 to the power 4. And that is just going to be equivalent to the power alone, which is exactly 4. So our offset becomes 4. So if you put in your formula log2 into brackets 2 to the power 4, you point that on the calculator, you'll be left with 4. Then after finding our offset, we need to find our, what next? Our index, or our line index. And we learned that the index is giving us a cache size all over the block size, and then the answer logged base 2. So what's the cache size that we've been given? The cache size has been given to be 1 kilobyte, where our block size, for 1 kilobyte, we write in its power of 2 equivalent, sorry. That's 2 to the power 10. So, and just, yeah, so 10. And then for the block, on the other hand, we do same. It has been given to be what? 2 to the power 4, right? It is 2 to the power 10 over 2 to the power 4. That's just going to be 2 to the power 10 minus 4, and that's equal to what? 2 to the power 6. And then we find the log base 2 of that, and then so we find the log of that. And then that gives us exactly what? Log base 2 of 2 to the power, that's just 6, like that. What this means is that we know our original to be that. We know this guy to be 6. So now all we need to do is find what's left, right? We need to find the remnant bits, and that will become our tag. So then the tag is going to be our total RAM size, which was 2 to the power 15 minus what we have taken out so far, which is our offset 4, and then 6. So that's 15 minus 10, and that just gives us 5. So then our final answer is going to be that our tag, our index, and our offsets are, you can give them their binary representations, by the way, 5, 4, and 6. Okay, no. Offset is rather 4, right? So 4 here, and then 6 respectively, like so. We have the answers on the next slide, so let's see if all right, so there we go. So the offset is 4, the index is 6, the tag is 5. That's correct. Okay, so please, does this make the concept I was trying to explain last week and then better understood? Is it clearer now? Here's another question. This one says the main memory is 64 kilobytes, followed by cache 2 kilobytes, and then finally block size of 32 bytes. We are supposed to find the values. So let's convert them into their binary. They are 2 to the power 10, 2 to the powers of 2, sorry. So then this is going to be exactly 2 to the power 16 bytes. We saw that in the last example we did. Then now we need for our cache, which is 2 kilobytes, and that's equivalent to 2 to the power 11 bytes. Finally, we need it for our 32 bytes. That's so that's block size, and it's equivalent to 2 to the power 5. So take note, this is bytes, the other was kilobytes. So don't get confused and say, oh, why is it that in the other one we said the 32 kilobytes equals something, then this time we're saying it equals a different thing. The kilobyte differ from the bytes. Kilobytes are larger than bytes. So with that in mind, let's start by finding our offsets. We know the offset is going to be the log to the base 2 of our block size. So that's just going to give us 5. And then we know that our line index, which tells us where exactly or which line we are going to be using, that one is going to be the, what do we call it, cache, which is 2 kilobytes, which we have converted to be 2 to the power 11. So 2 to the power 11 divided by our block size, which is 2 to the power 5. So 2 to the power 5, like this. And then that just gives us 2 all to the power 11 minus 5, like this. And then that's equivalent to 2 to the power 6. And then we find the log base 2 of that. And that just leaves us with 6. So that will mean that our tag will be the total we had for RAM. That's 16 minus the sum of these two values, right? So 16 minus 6 plus 5. 6 plus 5 gives us 11. 16 minus 11 leaves us with exactly 5. This means for this question, our tag is also 5. Our offset is, where is our offset? Our offset was already given earlier to be 5 too. And then our final line index, our line index on the other hand is 6. So the next question you're going to have to tackle with yourself. Okay, so if you have questions, please go ahead and ask now. All right, there we go. This is not all today's lesson will be about. You can see it's a fairly simple concept, so we can just breeze through right through it, and then we just go through that. So now here's the next question. You try it. It says main memory is 128 kilobytes, cache 4 kilobytes, block 16 bytes. You have to find tag, index, and offset bits. Are we working on it, or you need help with the conversions into the powers of 2? This one here is equivalent to 2 to the power 17. And this guy here is also equivalent to, this one is our main memory. It's 2 to the power 17. Whereas our 4 kilobytes is also equal to, so that's cache, 2 to the power 12. And then our 16 kilobytes. That's our block size. That's just 16 bytes. That's equivalent to 2 to the power 4. It will be Ankasa. Are we working or we are not? Okay. Mr. Venix, yes.
Yeah, so
You
for
can
my
speak. Go
offset,
ahead.
but for my
Yeah,
offset,
your
I got
offset
it.
was okay.
No, sorry, my offset was 4. Sorry,
Offset is
my offset
4.
was
Yes.
4.
Yeah.
Yeah, then my index was 8.
8 for the
My
index.
index, yeah, 8. Then my tag was 13.
The tag was 13.
Yeah, 13.
All right. All right. All right. That's powerful. Yes. I
Okay.
understand that.
Well,
Yes. Please continue.
yeah. So with my offset, I had 4.
Right.
Then my line index, I had 5.
Okay.
All right. Then with my tag, I had 13.
The tag was 13. All right. All
Yes.
right. All right. All right. So we have same offsets, same tags, but different indexes. All right. All right. Anyone else working, or can we proceed? If you'd like a little time. Okay, I think it's safe to say we should proceed. So looking at the parameters we've been given, yeah, who is speaking? Please go ahead. All right.
Okay, so my offset for my index was 8 and my tag was 5.
The offset was 4. Your index was 8. I can't hear you clearly. Can you please speak up a little, Mr. Bonham? 8. Oh, okay. And then your tag was 5.
5.
Always remember that the sum of these three should be equivalent to the total RAM size or the total memory size that we are picking from. So let's test a few to see which answers are correct and which are wrong before we even get into the working. So here, if I sum 4 plus 5, I get 9, and 9 plus 13 gives me what? Is it 22? So that's way beyond our 2 to the power 17. So no. If I do 4 plus 8, I get 12, and 12 plus 13 is 25, way beyond 2 to the power 17. So that's also no. If I do 4 plus 8, I get 12, and 12 plus 5 is 17. This answer is most likely correct. Now, we don't know whether or not it's correct, but we can say it's most likely correct. One thing I'm noticing is, for the most part, your tag and index were right, but your what do we call it? Sorry, your offsets and then your index were right. That's Mr. Venix. But somehow the problem was the tag. Mr. Nyako, I think his index and then his tag. All right. So let's see how the working was and see what we shouldn't be doing next time. Okay. So we start by finding our offsets. That's just going to be log 2 of this guy. So our offset is going to be 4. That one is easy. And our index is going to be the quotient of our cache, which is 2 to the power 12. And then our block size, which is 2 to the power 4. That's basically going to be 2 to the power and 12 minus 4. And then that gives us 2 to the power 8. So we find the log of this guy, and then our answer is 8. So now that we know that our log is 8, then it means we have found the value for our index. So if we know our index and we know our offset to be 4, then in order to find the tag, we just have to take the log of this guy That's the memory size. So 2 to the power 17, the log 2 of that will be 17. And we do that minus our 8 plus 4. And then that's 17 minus 8 plus 4 is 12, right? And that gives us 5. What this means is that our tag is now 5. So we have our tag to be equal to 5. And we have our offsets, our index. That's what follows. And then we said the index is equal to 8. So I think Mr. Wahin Richard was right. I was a Wahin Richard, I think so. So our index is 8, and then finally we know that our offsets from the start was 4. Like this. So don't forget the significance of these values. They play very key roles. We explained them in the earlier lesson. They are basically what are used for direct mapping. In the other mapping methods, though, some are taken out. So, for example, when we are dealing with associative and set associative, you might not necessarily need an index. You might not necessarily need an index. Since you're not being assigned a particular line and you can go into a random line, you might not necessarily need an index. So for those ones, you just be expected to find tag and offset. But mostly questions on these are focused around direct mapping. All right. One last example for you to attempt. So yeah, the answers are here. Offset for index 855. So looks like we're right. Let's see. Is there any question here that is creatively constructed? I think all are straightforward. All straightforward. So I wanted to see if there was one that was a little tricky to tackle. Okay, tackle this one and see. So those who are confused about how to convert these kilobyte values into their corresponding powers of 2, and let me help you out a little. You see, a kilobyte is basically 1,024 bytes. There's a kilo for the 1,024, and then whatever follows becomes a byte. So if you want to convert any value into its corresponding kilobytes, you need to consider the kilos separate weights and then the values bytes weights as well. So the kilo is always 2 to the power 10. So for a number like 512, the kilo is that here. And finally, we want the 512 itself. Coming in, some people are in the lobby, so. All right. Finally, and then we take the 512 itself and we convert that into its corresponding power of 2. So if I want to know the power of 2 of this guy right here, that's going to be our byte size. So 2 to the power of what gives me this. So we just saw that if you do, we know that 2 to the power, and what do we call it? So let's start big. 2 to the power 4. That gives us 16. We know 5 is 32. We know 6 is what? 64. 2 to the power 7 is what? 128. 2 to the power 8 is 256. And then 2 to the power 9 is 512. So this means that for this guy here, the byte is going to be 2 to the power 9. And in order to combine the kilo and the byte, you just multiply the two things you have here. So 2 to the power 10. So you do 2 to the power 10 times 2 to the power 9. And we know that when you're multiplying numbers and the bases are the same, you just add the powers, right? So it becomes 2 to the power 10 plus 9. And that's basically the same as 2 to the power 19. You don't need to show all this, just compute it in your head quickly. So you just change your 512 kilobytes to 2 to the power 19. So this means this guy right here is just 2 to the power 19. That's the equivalence of the memory or the RAM. So the main memory is that. And if you want to apply the same idea to the 16 kilobytes, you do the very same thing. So then you take into account what kilo stands for, that's 2 to the power 10. And then for the 16, we know that that's 2 to the power 4. So it just this way. So 2 to the power 10, 2 to the power 4. So you multiply them, it just becomes 2 to the power 10 plus 4, and then that will give us 2 to the power 14. So then that's 2 to the power 14. And then finally, we have the 64 bytes. Now, mind you, 64 bytes is different from the kilobytes. It has no kilo, so there's no 2 to the power 10. It only has a mere 2 to the power 4. So then that's hopes. So then it means our block size is going to be 2 to the power 4. Keep these parameters in mind, or better still, just you may memorize all of them, or you can learn how to convert them this way, so that you will not be caught like in the needed examination. Let's move fast. I also want to pause briefly and then talk about the assignments that were given. Quite a few
Hello,
of us
Prince.
have. Yeah,
Yes, sorry. You said the 64 is 2 raised to the power 4.
not 4,
Can you
it's
take that again,
14.
please?
Oh, sorry, 64 bytes. I was treating it like 16. Oh, thank you, sorry. So 64 bytes on the other hand is going to be, what is it? 64 bytes on the other hand is going to be 2 to the power, I believe, 6, not 4. Okay, I treated it like 16. Thanks for pointing that out. Sorry. So 2 to the power 6. And then the reason why we're not adding the 2 to the power 2 to the power 6. So having all these ones now, please compute tag, index, and offset bits. So whoever gave me the prompt time, thank you. But I've just let some people astray right now. Sorry. Mr. Kotsi, sorry. Go ahead.
Yeah, my tag was 5.
Tag is 5. Your tag.
Yeah, it was 5.
So if
Then
your
my
tag is
index,
5,
yeah,
index.
Yeah, my index was 8.
8.
Yeah. Then my offset was 6.
Offset was 6. All right. Okay, this is a plausible answer because they do sum up to the total space. So yes. Anyone else with these same parameters? Okay, I can see approval, so I think they agree with the answer. So let's work it out and see if we are right or we are confused. So we start with the first. We find our offset, and that's going to be the log of this guy right here, log 2 of this guy right here, and that gives us our offset to be 6 indeed, so that's correct. And then secondly, we find the cache in 2 bits. We already have that, so we find the index that's going to be cache divided by block size. So 2 to the power 14 over 2 to the power 6, that's 2 to the power 14 minus 6, which is actually 8. When we log it, we get 8. And then 6 plus 8 gives us 14. 19 minus 14 gives us the tag to be 5. So yes, that is absolutely correct. That's absolutely correct. So looks like we are on track. All right. So let's go back to the lesson. Complete just the little that's left, and then when we are done, I explain. When we are done, I give the details of the assignment to those who are asking the time. The deadline is nearing, so.
Yes.
And also, if you have problems regarding assignments and whatnot, and you need help, try to ask early, because the later you ask, that means more pressure for the person who is giving you assistance. If you ask earlier, then that's more time for them to help you. So please. Right. So it says, which mapping method results in the most conflicts? That's the thrashing. And why do you think so? So continuing with our lesson, please. Let's answer these questions. Which mapping method results in the most conflicts, which is thrashing, and why does it happen this way? Please, anyone with the answer, don't worry, you can just go ahead, raise your hand, and then share if you know the answer. I think 3 hands or 8.
Prince, please.
Yeah,
First off, I would like to, understand proper the meaning of trash. Like, can you give
the
us
thrashing. Oh, okay.
a briefing on the
Oh,
trash?
okay. I mentioned it earlier, but perhaps it's there. So let's talk about it. So you see, we talked about direct mapping, and we said in direct mapping, every single data value has a particular cache that it has been assigned to. What this means is that you cannot just get up and go to an empty space because it's available in direct mapping. This leads to something we call thrashing. Thrashing is basically conflict of who should stay and who should go, and it leads to someone always getting thrown off. Let's go back to the classroom analogy. a seat A is assigned to students 3 and then student 4. Student 3 and 4 comes to the class, and when they came, student 3 comes to the class first, he comes early, and he's seated on seat A. Student 4 also comes in. Let's assume students 4 and 3 have the same family political standing. The school holds them equal, so treats none with more favor than the other. What happens here? You wouldn't be able to tell who stays and then who goes, right? So then the CPU will have to make the decision based on who is needed more in that instance, and then the other one gets discarded. That process of discarding due to the conflict is known as thrashing. Okay? Mr. Prince, does that answer your question?
Yes, please. Yes, please. I'm fine. Thank
Yes, please. So I think even in saying that I have answered this, but what's the answer?
you. So it will be set associative.
Set associative, okay. So he says it's set associative and it results in the most thrashing. Yes, we need more answers. There are 3 more, there are 2 more. Let's see, do we all agree with set associative or there are more? Are you shy online? Hey. You're online and you're shy. Why shall you shy, Charlie?
Hello, Mr. Prince.
Yeah,
Yeah, I also think the answer is direct mapping.
direct mapping. Okay, that's interesting. Someone says set associative, someone says direct mapping. The question also asks why. So I'll go back to Mr. Prince. Why do you think it is set associative? It's a very interesting answer you gave. So why are we saying it's set associative? And Mr. Richard, prepare your answer on why you think it is direct mapping. Let's move fast. We have to tackle 2 or 3 assignments, at least a little of it. Yeah.
So I'm saying it's set associative because, like you said, the thrashing occurs when you have assigned a block for data, and then when they come, the block has been occupied already. Then
A line. Just one line.
Okay,
Yeah.
a line for data. All right, sorry for
Yeah.
that. So
The block,
let's
sorry.
say,
So the block, oh, continue, sorry.
all right, so let's say you've assigned a set of lines for maybe 2 or 3 data. Then they come, 2 come early. You assign only 2 lines for 3. Then the 2 come, the other one comes later. The thing is already full. So then that one will be discarded.
Oh, okay.
Or
Okay.
my analogy is wrong.
It's a very good way of thinking, but let me ask you one question first. Maybe there is a little confusion here. In direct mapping, do you believe that one slot can be assigned to 3 different data, or you think one slot goes to 1 data? Do you think it's 1:1 or it's many to 1?
In direct, I think it's 1:1.
It's 1:2. Okay. Okay. So I see where the confusion is. So perhaps it's an inconsistency due to the explanations or in the explanations I gave earlier. But in direct mapping, and if you look back at the diagrams that we gave for direct mapping, so look closely here. Look at this diagram for direct mapping. You see memory space L1 here has been given to block 2. Sorry, L1 has been given to block 2, yes. Same has been given to block 1. This very same memory space. So what does that mean? Block 1, block 2 will both come to this same memory space at a given time. And when they come, thrashing occurs. So then there's thrashing here. Over here to the thrashing, all right. However, the probability of it happening is a little less as compared to this. Because over here, we have 2 data that must go to the very same line. But over here, even if 2 data are coming in, they are not supposed to go to the same line. If one goes to this line, the other is allowed to go here. Thrashing only becomes imminent if there is another data that is coming to these 2 lines inside the set. Then that will mean that data will have to thrash something. But then you realize that we had to go beyond 2 data values in order for the thrashing to occur. However, here, just 2 data values were enough to make the thrashing occur. So that's how direct mapping has a higher chance of thrashing as compared to the set associative. All right. So, Mr. Prince, I see where your confusion was from. I see where your confusion was, right? So I understand. All right. So, Mr. Richard, you were right to say that's okay. So it says it's because it forces every memory block, into one specific line. If 2 frequently used blocks share the same target line, they constantly kick each other out. So if it is working based on spatial temporal locality and it knows that these 2 data values are important, who should I keep, who should I stay? It uses split second, or I won't say seconds because they work in nanoseconds or sometimes microseconds, to see who really is needed within this small space of time and who isn't. And then that's gets thrashed. So the one that is not needed in that space is thrashed, and the other one is maintained, and like that. All right. In direct mapping, where can a specific memory block be placed in the cache? In direct mapping, where can a specific specific memory block be placed in the cache? Yes, so let's attend to this one. Please, our ghost members, please. So they come and then possess people and then talk to us, okay?
Okay.
You
The
never
right
speak.
answer is 2. I think.
The answer is 2. It says in one specific line only.
Yeah,
Yes,
I think
in
so.
one specific line only. Excellent, excellent. So let's see that. So yes, you are right. You're right. The right answer is very good. Which mapping method requires the cache controller to search all the lines simultaneously just to find data? So this time, data has already been held inside the cache space. And then due to how it was stored, it has to read the entire cache space just to find the particular data and where exactly it is. Which mapping method requires this?
Fully associative.
The fully associative. So it makes the control units do over time. That's right.
Yes.
Set-associative mapping.
Set-associative, eh? So then the correct answer is actually fully associative. So let's see. Set-associative, on the other hand, it combines both the freedom or the flexibility of the fully associative, but with the restriction of the assignments given inside direct mapping. So this means that instead of searching the entire cache space just to find one line of cache for a particular data, you are reduced to searching a particular set. So maybe in that set, instead of searching through several million different spaces or several thousand different spaces, you are only limited to searching about 4 or 5. So that's what the set associative does. So it reduces how much the CPU has to search to find where the data has been stored. So the fully associative is the one that requires that all lines are searched and at the same time too, simultaneously. And that's why it makes the machine slower to retrieve the cache data. Okay. All right. If a cache
Mr.
has
Prince,
1,000,
please,
yes.
can you take it away?
Okay. So I said it's not set associative. Why? The reason is, let's assume these things you are seeing right here, okay, are cache spaces. Okay, let's assume this is 1, this is 2, this is 3, this is 4. Now, in fully associative, let's say all of this, everything you see here is one line. All of this is one line. All of this is one line. All of this is one line. Just one line of cache, okay? Just bear with me. Now, I put data into this. The data comes and then randomly sits in any of the empty spaces because that's what fully associative is about. There is total flexibility and freedom. So it just comes and then it sits inside space 3. Now, if I want to retrieve the data that is being held in 3, what will I have to do? Since that data is not tagged with a particular line index, we don't know where exactly it has gone to. So in order to find it, what must I do? I must simultaneously or all at once, because I need it fast. The CPU has to work fast after all. I must all at once search all these 4 lines together just to find the data that I'm holding at this spot. That's in fully associative. So then I must search all these 4 lines. I search this line, this line, this line, this line, all in one go, and then I find it to be standing at line 3. Then I can retrieve it and then give it to the CPU. That is for fully associative. Now, what happens in set associative? Think back again to what I just said concerning the cache lines, but this time, look at this line as a set that is holding 1 cache space, 2 cache spaces, about 3. Okay, so then think of this about as a set that holds 3 different cache spaces, and this one also has a set that holds 3 different cache spaces. Now, let's say a data value is coming here. That data value has been assigned a particular cache set. So in set associative, we don't assign lines, we rather assign sets. You've been assigned a particular set. So maybe the set you are assigned is assigned a set 1. In set 1, there is cache line 1, cache line 2, cache line 3, cache line 4. The data will now come and sit in any of these random cache lines. Maybe cache line 4 is sitting here. Remember, it came and it picked the random cache line within a set to sit in. This means CPU doesn't necessarily know where exactly it is because it is not indexed. So for that reason, in order to identify that particular data, we must now go to the set where it's held. So you see, the difference is that in this one, we don't have to search all the separate cache lines, but rather we only search the ones that are within the set because we know that that data was assigned to set 1. This narrows down the search area, making it so that the searching will only be done for a shorter period of time, and also it will be faster too. So then set associative, you see, it did the assignments all right, but instead of assigning to a line, it's rather assigned to a set. And within that set, the data went to a random line. That random line motion is the associative, right? And then the direct mapping part of it is the fact that it was assigned to a set. Combines both. Is that clear?
Okay, thank you.
Are you certain it's clear?
Oh, sure.
Not that clear though.
Come again.
I mean,
Auntie
not
Viola,
that clear.
not that clear. Let me draw you a
Hmm.
diagram and then you understand. Yes, sir, 209, no. Ebefaboko, 203. Okay, so you'd also need a 203. Don't worry, even if the time is up, I'll spend about 15 minutes telling you. It is nothing complex, okay, so it won't take much time. Okay. To those who are questioning this, okay, I don't see why we've come this far and then the questions are now coming. Okay, it's good, I guess. It's good. So I'm going to draw these as cache lines. Coming in. So let's draw some cache lines. Let's say this is 1, this is 2. They should have the same size, okay, and this 3, this is 4, this is 5. All these are lines in cache, okay? Remember, those cache lines are basically the spaces in which data are held, okay? Now, if if a particular architecture uses direct mapping, let's give all these cache spaces, what do we call it? Names, okay? So let's say this is A, this is B, this is C, this is D, or line 1, line 2, line 3, line 4. That's basically how they are called. But let's just use alphabets. This is E, that's F, that's G, that's H, that's I, J, this is K, that's L, this is M, this is N, this is O, and this is P. Now, let's see the data that I am holding coming from memory here. I am bringing it into the cache. If I am using direct mapping, every single data is assigned to a particular space. That's why we use the line index. So the line index tells us that we are inside this particular line, and that's where we are always going to be. So for example, with this line index, if a data is coming, if this is the data, and then the line index that has been given to it is E. This means that this data will only ever be allowed to go to E, and it will always be E and nowhere else but E. That's direct mapping, and that's why it is fast. The controller doesn't have to browse through the entirety of the cache system just to find the particular line, but rather the data just flows directly to where it is assigned. That's direct mapping. Exactly. Now, let's look at fully associative. Let's take the same data that was coming, this data. Now, in fully associative, the problem is the data can go anywhere it wants, and then that's not a problem from the start, actually, because it's flexible. It means the data can choose any empty space if something is occupied. So the data can come and it can be in E, or instead of going to E, it might choose to be in M. Or maybe instead of going to M, it will choose to go to P. Like basically anywhere goes. Instead of going to P, it can be at D. Anywhere goes like this. So we don't know where exactly the data is going to be held. So let's assume that the data actually went all the way to L right here. If the CPU wants to retrieve this data, or if the controller wants to retrieve this data and give it to the CPU, what must it do? Since we don't know where exactly the data is held, it must continuously search A, E, 1, it has to search I, M, all of them together before it identifies that, oh, this data was being held in L. However, in direct mapping, because the data had an index that was pointing to E, if the controller wanted to retrieve it, it just has to go to E and do what? Take it out. Is that understood? Before I add the set associative, do you understand the direct and then the fully now?
Yes, please.
Okay. So now knowing these two, so direct assigned to particular space, so no searching, just fast. So if you are retrieving, you just go to the place where it was assigned, you take it out. Fully associative, it can be anywhere, so you have to search every single place just to find where it is being held. Then there comes in set associative. The disadvantage of the direct mapping is because each data is assigned one spot, if I am having two separate data, and then maybe they are both assigned to spot E, like this. The first data might be here in spot E, but because this one is also assigned to the same spot E, it cannot go in I or M even if they are empty. So what this means is if E and then if the first and second data are both needed as that instance, one has to be thrown away and then the other has to be taken. So then in order of priority, the one that is really needed will be kept and then the other one will be discarded. This is called thrashing and is due to the conflicts that is caused due to the limited number of cache that has been assigned to particular data values. So that's thrashing. Is that clear? And it leads to a lot of misses. It leads to a lot of misses because some data will just be thrown away. And when the CPU needs to use that data in that instance, it might have been discarded. So it leads to a lot of misses because data can be easily discarded. So this is what the direct is about. In the fully associative, on the other hand, when this data is coming, because they have not been assigned particular spaces, when it's coming and then the CPU, also when the data is coming, mind you, in fully associative, CPU searches again. So when we are bringing data in fully associative, CPU first searches to see which space is empty and which one is full. So let's say it searches and it realizes that, okay, E is full. It searches everything at once. If it sees that E is full, then it tells the data just chooses an alternative path to go to. Maybe it goes to M. That's fully associative. What this means is, since the data went somewhere else, if the CPU wants to get back that data, then it has to now search the whole system again to find and pinpoint exactly where that data went before it can take it. Doing this will mean it has to go through several different separate cache all at once, and that is very tasking. Sorry. Then we have the set associative. Set associative now groups all the separate lines into sets. So let's say this whole line here has been grouped as set 1. All of this has been grouped as set 2. All of this as set 3. And all of this as set 4. So they are still your RAM lines, but then they are all now tagged with different set numbers. If a data is coming, in set associative, that data is assigned a set, not a line, but a set. So let's say this is assigned to set 4. What this means is that this data cannot go into set 1, it can't go into 2, it can't go into 3, it must always go into 4. The difference between this one and then direct mapping is once it enters 4, it can choose to go into M or N or O or P. Basically, everything inside 4, as far as we are within 4 goes. So that data can go into M, it can go into N, it can go into O, it can go into P, as far as it's going to 4. So then this time the assignment was done to a set of lines, not to a particular line, but to a set of lines. Now, if the CPU wanted to do this assignment, remember, some data can already be held in N, right? And maybe O can also have data. So if this data is coming, it must not come and replace any of these guys because we want maximum efficiency. So in the set, the CPU will now search, but it will not come and search 1 when the data is going to 4. It will not come and search 2 when the data is going to 4. It will not come and search 3. That's a waste of time. It basically narrows the search area to what? 4, making it very efficient. So instead of having to search 1, 2, 3, so instead of having to search 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, plus the 16, it rather only searches 4. And after it searches the 4, it realizes that, okay, these 2 are occupied. So you pick either M or P and go and stay inside. So the data now decides where it goes to. Or basically the controller now pushes it to a random space. So maybe it pushes it to P and the data is now held in P. This means if the data is being retrieved, what must the CPU do? Since it knows that that data was tagged with 4, it has to go to set 4, just set 4, and search for the spaces inside set 4, ignoring set 1, 2, 3. This is the set associative approach. So now, from what we have just discussed, which one do you think will lead to a lot of misses? Which one do you think will lead to a lot of misses? Is it the direct? Is it the set associative? And is it the fully associative? Which one? A lot of misses in the sense that a lot of data will not be found when it's needed. Which one will lead to that?
Something it could be direct.
It's the direct, exactly, because it leads to a lot of thrashing. Which one do you think is the most efficient? Is it the fully, because fully associative allows data to go wherever. So this means it can be easily, once data comes in, it can find somewhere to be because everywhere is open. Which one do you think is more convenient? Is it fully set or direct?
It's set.
Is the set. So why do we
Yeah.
think it's set?
Because set when it carries data, it goes anyway. Like since they're all in how do I
Come
mean?
again?
I
Come
name
again?
I name set.
Yeah.
Reason being that it carries data straight, it's set word and there's no data and it stores its values there.
So it goes to the particular set that has been assigned to it, right?
Yeah.
So how is this more advantageous? Because as you said, when it goes there, it also searches to see which is empty and which is not before it assigns it a spot or before it goes into a spot. Let me use it goes into a spot. How is this
Mm.
advantageous over the fully associative? Because in the end, that's what we search, we find, we give a space.
All right, so I
How
think it's the fully
So fully
Hold on. Should
associative,
I?
yes.
but antivirus,
It's
I
the
am
fully
swaying you easily. Oh. I am swaying you. As a Christian, your faith must be strong. I'm swaying you. Okay.
Hello,
Who
Mr.
upset to
President.
talk? Yes, I'm
Mr.
listening.
Prince.
Yes.
Okay, so I think all lines in the selected set can be searched at once.
Mm-hmm.
Yeah.
That's right. That's right. Yes,
So
you're right.
so the I
please,
think
please, that's the set, right?
Yes, in set. Yes. So in the
Okay,
particular set,
okay.
yes. Even inside the fully associative, the CPU will search all lines at once. But the cost is because we are searching all lines at once, we are slower in our search. But every single line will be searched at the same time. If it takes us 3 nanoseconds to do that, we are still going to do it anyway, but every single one will be searched simultaneously. So an electric signal is broadcasted throughout the entirety of the cache system. Every single component gets searched. checked in that particular instance. Slower because we are checking more in fully associative. Faster because we are checking fewer in set associative. Indirect mapping is the fastest because we are not doing any checking. We know you are supposed to be in E, so go to E. That's it. But there is a trade-off. Indirect mapping is fast. However, there are a lot of misses because it's very restrictive. We must go to E. In fully associative, it's slow. However, it's very flexible because everybody can go wherever. So there will be barely a chance of any thrashing or conflicts, right? In set associative, though, it has the speed. Even though it's not as fast as direct mapping, it has the speed because we are not searching the entire CPU at once. It also has the flexibility. Even though we are not using the entirety of the CPU, we are still allowed to get different spaces to store the same data instead of having to store one data in a particular space. So then the best one, the most convenient one that most modern systems use is actually the set associative. Since it combines the flexibility of the fully associative with the assignments of the direct mapping. Therefore, it gives you optimum speed and optimum location too, or optimum assignments. I don't know how I should put it. So you see, the most advantageous one will be the set associative. And then this is why the question that I was asking, which one requires that the CPU is simultaneously searched at once, like a lot of CPU spaces? The answer is what? What do you think the answer will be? So from what we have said, the answer is what?
Please
What's the
come
question
again with the
again?
question.
Right. So the question that we saw on the last slide, this is it. So from what we just talked about, it says which mapping method requires that the cache controller searches all lines simultaneously just to find data that has been stored away. All the lines, not some lines, all of them.
So that would be fully associative
That's the fully
mapping.
associative mapping, exactly. It's fully associative, and that's why it is a disadvantageous mapping strategy because we search everything so then speed. But then the advantage of it, so you should know that there are goods and bads to it. But because the set associative stands in between, is the most efficient one to go with. So we have come to the end of this lesson. So yes, the correct answer is the fully associative, as you can see indicated with a thumb here. So look at this one. It says if a cache has 1024 lines, how many bits are needed for the index line number? It has 1024 lines.
32 bits.
It's how many? 32.
32 bits.
32 bits. What brought you to that conclusion, Lady Vida?
Ah, um,
Is the highest there.
That's a wicked way to think. I'll say highest there. Okay, let's analyze this. 1024 basically refers to something, right? We know that is just a kilo. Yes. Now
yeah.
look here. With this particular
So
one,
it's
it's a
10
kilo.
bits.
Yeah, so it's kilo of the bits, right? Good. So now if we want to convert that back into the bits, we just have to see 2 to the power what gives us 1024. And then we looked at it when I was explaining the conversions into the powers of 2. So 2 to what power gives us 1024?
1
10.
minute.
It's 10.
No, it can't be.
Still 10.
It,
It's 2 raised to the power 10.
Oh, it actually is. Why that? So let's start from the lower side. So let's see. So you see 2 to the power 2 is 4, right? And then 2 to the power 4 becomes 2 to the power 3 becomes 8, 2 to the power 4 is 16, 2 to the power 5 is 32, 2 to the power 6 is 64, 2 to the power 7 is 128, 2 to the power 8 gives us what? 256, 2 to the power 9 gives us 512, and then 2 to the power 10 is double of 512, that's what? 1024. So it's
all
actually
right,
2 to the
so,
power
so,
10.
so
Yeah. So 10 bits.
into the past.
Yes. So then we've come to the end of our lesson. The session was very interactive, and then I think we have fully understood the concept that are being taught. I'm very grateful that you raised the questions that you raised, because honestly, I was thinking that even though the older lessons were a bit on and off due to the power, the ECG thing that I'm facing, I was thinking that we had understood the concept, but today has shown me that we had to go back. That's very, very good. So
Yeah, but
thank you
Mr.
for coming.
Prince,
Yeah.
that thing that you explained earlier, the set, this one, the direct catch the things, I will
Mhm.
meet in your DM, then you explain more thing because because
Hey,
that
after all
one,
this,
I think the answer should be the set.
associative
Yeah,
there.
yeah.
Okay.
So
All
you
right.
you meet in a DM and talk about it.
All right. Okay. Don't worry, we'll meet in the end. But
No, we are
everybody, I want
doing
you
the
to
class
know.
here. So no, we are doing the class here. So to explain it here.
So everybody, wait. So how many of us have now understood why the fully associative is the one that requires that you search everything?
I do, but then are you not going to talk about the assignment? I think some people wanted you to talk about the
Yeah,
assignment.
that's right. That's right. Hey, let's do that first. So please, assignment people, sorry, let's discuss the assignments. I think at this point I
Yeah.
should let me end the recording. So give me a second so that it doesn't worry our, you know, all right, done. So I'll need a question. Okay, so okay.